I'd like to welcome you all to Stellafane Convention this year. I hope you're having a good time. You're at least not broiling in the sun. That's the good news. I hope you brought your umbrellas, because I think you're going to need it a little later. But tomorrow promises to be a beautiful day. In the meantime, we have some interesting talks for you to listen to from some very, very exciting speakers, so I'm glad you're here. One announcement I want to make first is that we have talks tonight here. They're informal. If you want something you want to talk about, or have an idea, or know somebody who wants to talk, there's a form, a little form. They're back on the table where Paul Lilly is sitting by the window for the kitchen, and just fill out the form and take it up to the T-shirt, where they sell the T-shirts. They'll collect all the forms, and that's how, they'll give you an opportunity to say something if you want to. The first speaker for this afternoon, I would like to introduce to you Al Takeda. He is the lab manager of for the Electronic Instrument Design Lab at Harvard University. He's going to be talking about deep sky imaging with a digital single lens reflex camera, DSLR camera. And it says here, you probably got it in your program, while the dedicated thermally protected cooled TEC large sensor CCD camera is the instrument of choice for the professional advanced astro imager, the prices can be prohibitive for most astrophotographers. The alternative is the DSLR, which can double as a daytime and nighttime astronomy camera. In this presentation, Al will discuss the DSLR camera's ability to capture D-sky images. Topics will include the type of DSLR to choose, which lenses would work, adapters needed for a telescope, what targets to choose, the imaging session, and post-processing of the images. Al will demonstrate those capture techniques in real time, Friday evening, Saturday closed out, using the AMIT system. So we'll probably talk more about that. So without further ado, now.
Okay, thank you. All right, let me just get things started here. All right. So, my talk tonight, of course, we've seen, this is an image, of course, taken with a DSLR camera. And, of course, these DSLR cameras can, of course, be used during the daytime when you're traveling to these exotic places around the world. Of course, we can, you can also take pictures of people, interesting places, even wildlife photography with a DSLR. It's a very versatile camera. But, of course, we're going to talk about deep sky imaging. So let's actually talk about the DSLR camera. Basically you have a removable lens. You have light comes in through the front of the lens, bounces off the mirror, up to the pendant prism at the top, back into the eyepiece, and then you can, view what you want to take a picture of. And of course, when you shoot the shutter, press the shutter, this mirror flips up, and then the sensor's behind here. And that's the general DSLR camera. There are a lot of DSLR cameras out there, as you know. I mean, there are a multitude of companies making them. Some camera companies, some not. So in this talk, we're going to try to narrow it down just a little bit. And I have to excuse, I'm only going to talk about one type of DSLR camera, and that's the Canon line. I'm used to Canon. I've had Canon cameras since the old film days. So this is actually my camera. It's the Canon 20D. They don't build this camera anymore. Okay, well, imaging camera, the Canon 20D, it's, of course, is a DSLR. It's a daylight single-shot camera, so I don't have to worry about filters. You just take one shot and you get it. It's an 8-megapixel camera, which is odd today. You have 12, 14, who knows how many more megapixels they're going to make. And it's low electronic noise. But what really makes it special for astrophotography is these two things: the mirror lockup and the USB and shutter control connections. So let's actually look. Now here's the purchasing advantages of a DSLR camera. And all these facts make it really nice to own one. Of course, you can spend a lot of money for real astronomy CCD cameras. In this case, with a DSLR, it could be as low as $350, or it could be as high as $3,000. But again, do you want a professional grade camera or one of the lesser consumer cameras? It's fine. It can still be used. Even the $350 consumer grade camera that's used for the beginner can still be used. It also has a large user base. There are a lot of people using the digital SLR, so if you have a question, you can ask people, how do I use this particular function or control? So, and many lenses can be used, obviously with that camera line. And if you decide, astrophotography isn't for me, and you really don't want to have this camera, you could always sell it. There are a lot of people who, in the used market, would love to get this camera. Well, let's talk about the sensor that is in my camera, the 20D. It's a CMOS sensor, and CMOS sensors are used instead of a CCD camera, but they still can be used, and they can be manufactured on the same fab line that a lot of the electronic parts are made, and so it's actually less expensive to produce a CMOS sensor than it is a CCD sensor. And here are the various specifications for the chip. And these are 6.4 micron pixels, which are fairly large for the modern DSLR camera. And we'll talk about the pixels a little bit later. All right, here's the sensor. This is the actual sensor that's in the camera. And you can see, and now right below it, you can see an IR blocking filter. That kind of limits you with a lot of the hydrogen alpha, the red colors you see in a lot of the nebulas. Well, this filter, which is in front of the sensor, the CMOS sensor, limits you slightly. But, you can still do stuff, and you'll see that in a few minutes. All right. All CMOS sensors, all CCD sensors, they're monochromatic. They're black and white. So in order to see them, to see the color, the one-shot color, they have these filter arrays. And this is just an artist's conception. And you see, blue and green and red filters, the RGB set. This is a bare array. And I want you to notice something. There are more blue and green sensors than are red sensors. And that's because the monochromatic CMOS sensor is very sensitive to the infrared. And so if you had the same number of red sensors as blue and green sensors, if you take a picture of somebody, they'll have sunburned skin. They'll be red colored, and then you'll have to filter that out. So the way that they get around this problem is they actually make fewer sensors. They actually manufacture fewer sensors on the filters. Okay, well here are the requirements that we all need for astrophotography. And this applies mostly even to CCD cameras, real astronomy, dedicated astronomy CCD cameras. And of course, manual camera controls, mirror lockup. You need to lock that mirror up to prevent vibration. Remote shutter release or USB interface, so you can control the camera. Because you could use the remote shutter release, and you just keep pressing the button, and it becomes a drag after the third shot. So you want automatic features. Of course, live view, so a lot of these new cameras have what they call a live view setting, where you can actually see what you're actually trying to image. Removable lenses, of course you have to take the lens off, you put other lenses on, or attach it to a telescope. Large pixels, we'll talk about that later, it's sensitivity, it's a sensitivity problem. And telescope adapters. So let's actually go through some of these devices. There's a remote timer. Let's say you don't want to use a computer. Normally I attach my system to a computer. But if you want to, you could use one of these remote timers, and it has all the interval timing, shutter release, exposure control, delays. It has all of that. And you can use this if you want to save, spend less money. And this is only about $150 roughly. It's not that expensive. Okay, so unfortunately I have a 20D, which is a pre-40D model. So I can have two connections. You see two cables out of here to control it. One is the shutter control cable, and the other is the download cable. The more modern cameras only use one cable. Okay, lenses. What lenses can I use? Well, actually, most of the lenses can be used. Obviously, you want to have fast lenses like f2.8, f1. That'll allow you to take very fast images and be able to take them quickly, so you don't have to sit there and open the shutter for a very long time. But they're expensive. Now, the one thing, if you're really serious about getting into digital SLR imaging, you want to have what they call the EF lens series out of Canon. Now, I'm going to just talk about Canon. And by the way, Nikon makes great cameras for astro imaging, Pentax, etc., Fuji. So I'm using Canon because I'm used to it. I understand the Canon line. Now, there is this line called EFS. And what it is, it extends back farther into the pentaprism body. And you don't want that. You want the EF lenses because of that, so that don't extend back very far. And we'll talk about that later, why that's a problem. And the other is, of course, they're higher quality. The EF lens series is a higher quality lens series. Okay, let's talk about pixels. Well, these pixels, and what it is, I've got this off the web with all this information, and it actually talks about the pixel sizes on the sensors. Well, what I did is I've put these down into the professional series at the bottom, and then, of course, the full frame cameras here, and then, of course, the mid-level 10D, 20D series, the D series. And the top is the Rebel series, which are the lowest cost series. You know, you can buy one for between $350 and $500. And you can still do great work. But I want to notice something about this. You notice that the sensors, as the amount of pixels, megapixels have gone up, I mean, look, 18 megapixels, that's a lot of pixels. The sensitivity has actually gone down because the pixel sizes have actually gotten smaller. As the pixel sizes get smaller, it gets less sensitive. And here's why we have to worry about sensitivity. Because if you have one of these two situations, an undersampled situation in which the stars become blocks. The other is, of course, you've got great resolution, but you know the chip is less sensitive. Also, you have more resolution than the sky. You know, sky conditions can warrant. Well, there is a formula, and I often ask, you know, is this digital SLR good for my particular scope? Well, my scope, of course, is 180 millimeters f2.5 scope. And are they matched? You know, is the sensor matched up to my telescope? And there is actually a formula to calculate that. And the calculator is arcseconds per pixel equals C in arcseconds times the focal length in millimeters divided by 206.3. And what that gives you, when you actually do the calculation, I did it for 3 cameras. The 1D camera for professional series, Canon, the Canon T3i, and the 7D, which are the most modern D series of Canon in the mid-level cameras, and the 20D, which is my camera. So I did the calculation and said, okay, well, 8.2 micron pixels, you know, bigger pixels. So it's undersampled. So you could start to get blocky images. But you just start to, depending on the night. The T3i, the mid-level, the 7D, are 4.3 micron pixels. And if you look through the math, it's smaller pixels. And so it's slightly oversampled. So higher resolution, but less sensitivity. And now my lowly 20D, 6.4 micron pixels. But if you notice, smaller pixels, slightly oversampled. That's the trick. It's slightly oversampled. Which means that it's got very good resolution, but it has higher sensitivity. And that's what you want in a digital SLR camera. You want that balance. On the other hand, any of these cameras can be used for digital SLR imaging because it isn't too far out of the range. It's very close. Your seeing will actually determine how good your image will be that night. Okay, so let's talk about adapters. Well, the reason why you want a digital SLR is you can take the lens off and you can put adapters and you can actually attach it to your telescope. Here are the 2 main adapters that I use. The left side is, of course, the 2-inch nose piece. You attach it to your DSLR camera, and then you can slide it into the 2-inch nose piece of your telescope. And you want the true tube nose piece because it's very wide. It's as wide as they can get. I mean, they cut that thing awfully thin. It's a very thin adapter. But you get no vignetting, you get no light cutoff on any part of the sensor. The other is one on the T adapter at the bottom. And the T adapter is nice, which you can attach your telescope, you just click it in place. You don't have to worry about anything coming loose on the nose piece, it won't slide off. You click it in place, and that's it, you're finished. Here's my setup out in the field. And as I frequently tell people, it's my portable observatory. I practically have everything needed that a normal person would have in his observatory, a real building. So let's actually talk about some of the things that I have in this observatory. Of course, I use a Loxmandy G11 German equatorial mount. And yes, it's not the best mount in the world, but it's not the worst. It's kind of in the middle. I have to do a lot of TLC, tender loving care, to keep that thing running and keeping the gears tight and make sure it doesn't get big periodic error. But it's less expensive than a lot of the other mounts. Of course, I use a guide scope. I have another guide scope attached to it with a guide camera. My 20D DSLR. I also use dew heaters. This area, definitely, with the humidity and the dampness in the night, you definitely need dew heaters. Laptop computer, and of course, guiding imaging software. Here's a close-up. You can start to see. Here's the guide scope. It's a 90 millimeter, and the main scope with the DSLR attached. Here's a close-up. Okay, here's my telescope, Takeda 4180. It's a 7-inch hyperbolic astrograph. And one thing about astrograph, well, this one is the hyperbolic primary and secondary mirrors, and it has a flat field lens actually in the focusing tube. Keeps, when you look at the image, the stars from one corner to the other are circular, they're round. They're not oblong, there's no coma. Also, this is a real astrograph. It's a photographic-only instrument. You can't put an eyepiece, well, you could, but everything around the edge will have coma, really bad image, bad viewing. So you don't use it. This is a real photographic-only instrument. And I bought it this way. I take photographs. So the guide scope is a 90 millimeter. It's an acronym. At 5.6. You don't have to have a great scope. Whereas as long as the stars are circular, there's not a lot of really bad artifacts in the optics, you can use it. Inexpensive. I think it was only like $250 or so. So don't spend a lot of money on your guide scope. Next is the CCD auto guide. Well, I recently upgraded from the old ST4, which had these 2.5 millimeter square pixels. You can't find anything with that thing. And also, it just got so old that it was having some trouble guiding. So I picked up this camera. It's an 8300, ST8300, Santa Barbara Instruments Group camera. But one nice thing about it, it's got a 2-degree field. I can get guide stars anywhere. Well, here's my camera. It's a 20D DSLR. For some of you to notice, there's actually a filter in here. That's a light pollution filter. Of course, for this region, maybe not Vermont, but where I am in Massachusetts, you get light pollution gradients everywhere, towns nearby. So what I did is I actually bought an astronomic light pollution filter. If you use an EFS lens, remember I talked about the EFS lenses? I can't use this setup because the lens would actually, the back of it would actually hit the filter. So that's why I only use EF lenses. I knew that I would be doing this someday. Even 4 or 5 years ago, I knew I would be doing this. So I made sure that I had that provision where I wouldn't get the back of the lens sticking into the mirror box. All right, here's the imaging software I use. Of course, the camera control, I use Images Plus. It's an older version, but it works just fine. Auto guide control, I use CCD Soft. It's the SBIG, Santa Barbara Instruments Group software. Exposure histogram and focusing. We'll talk about more about that later, but I used what came with the Canon camera. It came with a planetarium program to get guide stars, find my field of view, what I'm going to shoot that evening, and I use the Sky version 5, which is of course another older program, but I don't need all the fancy gizmos that the Sky X version has, so this is perfectly fine for now. Okay, so we're going to talk about the imaging workflow, what I actually do to bring put everything together and actually start the imaging session. Of course, you assemble the mounts, you attach the telescopes, cameras, electronics, and of course the miles of wire. And of course you balance the scope, and this is something you should all know. East side heavy, that's my little acronym that I use to tell myself, anything, that east side of the mount has to be heavy because I want the gears to push against the mount so I get very little periodic error. So it's always pushing. Whether the telescope is on the east side or the counterweights are on the east side, you want it heavy. You want it a little bit heavier so that it's always pushing against the gear and you don't get that shaking of the periodic error in your gears. because all gears are never put out perfect, so you have to auto-guide to get them out. Of course, port line the scope, and the mount, and port line, and star drift, and of course, this is the reason why we have the star drift. Okay, so now let's actually start setting up the computer, the Images Plus programming. So you launch Images Plus, you connect to the camera with the cabling control, and then of course you select the destination target. I always like to take my images from the camera and push it right into the computer. I don't like to keep it on the camera. Another thing I like to do is now let's talk about exposure. Well, these are all the images that you have to take. Flat field images, light frames for focusing, exposure settings. You have to take many light frames to get exposure settings. The subject matter, of course, dark frame images, and bias frames. So let's start to talk about what the calibration frames are. And these are, you must do it for every shot, because you're going to get a lot of artifacts in your pictures. The first one, of course, is flat fields. And you take a picture of an evenly illuminated frame. And this will prevent vignetting and any optical, artifacts in your imaging frame. And what I do for flat fields, and I just want to show you real quick, is it's a technique. What you do is you put an evenly illuminated, let's say a white surface like in front, a translucent surface, look up at the sky. It's essentially a sky flat. So I pointed at the sky, make sure there's no light going into the side. I do it after the sun is set. I usually point to the north. And there's a technique, and they call it a t-shirt flat. A real t-shirt. You actually put it in front of the telescope, stretch it out using bungee cords, put it taut, and it basically diffuses the light that's coming in. Next, of course, the dark frame. And that's the heat noise of your camera system, the ambient temperature. You have to take a picture of the exact same exposure as your light frames, your subject frames. The last is bias frames, which is shortest possible exposure. For my camera is 1/8,000th of a second. And what you're doing is you're basically the electronic noise in your camera. So here's a flat frame. Now, I've stretched these images out so you can see it. Now, normally you can't see this much detail. But for just a demonstration purposes, I've done this. Up here, that's a histogram. Something else. The histogram will become your friend if you're doing digital SLR, even if you're doing CCD imaging. And what the histogram is the lightness level. It's the brightness level of your image. It goes from 0% to 100%. Your exposure should always be, for your flat frame, flat field, it should be roughly 30 to 40%. Next, the dark frame. It's the heat noise of the camera. Now, right here, you see this donut right over here? That's the amplifier of the camera. Some cameras, a lot of the newer cameras don't have this. And if you also start to notice, you see all these red pixels, all these little dots across. That's also bad pixels, stuck pixels, dead pixels. It's also the electronic heat noise from the chip itself. Bias frame. Again, this is a stretch image, but you can start to see this is the pattern noise or the electronic noise, and you can actually see the grid pattern of the CMOS sensor. Focusing. Of course, what I like to do, my telescope has a nice spike on it, and it has a nice slider. And so you can use it to get focusing. If we wanted to get good images, you have to focus. Launch the auto-guider software, select the guide star, and your auto-guider should be between 1 and 4 seconds, because if you're less than 1 second, you're going to chase scene. As the star, if you have a really bad scene night, it's going to boil away, and it's going to bounce, the star's going to bounce around, and the auto-guider will actually try to track it. You also don't want to get more than 4 seconds, because what will happen is the scope block will actually move, and then it'll try to correct, but it'll correct too late. And here's an example of it's what I call my dog bone picture, because I had really bad periodic red line. But that's what it does, get rid of your motor drive fluctuations, periodic errors. That's what you have to do with all your auto guide. Alright, so let's talk about Images Plus. Alright, so you enter the exposure parameters and you go for exposures. And again, here's your histogram again. Again, you have to be your friend. Notice it's a roughly 30 to 40% brightness level. Because if it's too bright, over 50%, you lose detail. If it's too dark, you can get noise. Alright, so, and of course, your imaging optics, your imaging train, and the sky you have that night will determine what exposure you use. Sometimes it can be as short as 30 seconds, and maybe as long as 10 minutes, who knows. Every night will be different. Alright, now you just put all the exposure information, and you actually start your guide route. You actually start your guide, you start everything up, and now you take as many pictures. It's all about signal to noise, if anybody knows about that. You have lots of signal, but little noise. You'll never totally get rid of noise. Noise will always plague you. But it builds up a lot slower than the signal will. So that's what you want to do. Take a lot of pictures, and you get more signal, less noise. Alright, let's actually go through the image process workflow. So I use Images Plus because it has a really nice automatic image processing feature. And basically you enter your light frames, dark frames, flat fields, you know all the things. I hope you've been taking pictures with all of these calibration frames because you're going to need it. And of course you select the process button, it's going to convert it to a bare array format. And then finally when it does all the combining, it will then output a color image again. But it's going to start out as a grayscale bare array. Then you got to align the images because you may have some slight variations in imaging that night. For whatever reason, maybe the guider didn't keep up or whatever. So you select various stars, you have a couple of stars here to either do translational, up or down, left or right, or rotation and scaling. Okay, then finally, when that finishes that process, remember, this process may take 10-15 minutes to do. Now, we're up to this point, and we're maybe 15 minutes into the processing, depending on the speed of your computer. Now we do the combining. This is where the action is. Finally, we're going to get all the calibration. Everything's going to be combined. So it's, okay, here we go. We're going to get a combined loop. Make sure that you check off auto display. And we're going to get a great picture, right? And here we go. I don't see anything. Well, information is there. It's hidden from us. Because what we have to do is we have to actually stretch the image. Because the information is in the image, but it's not right up front. And so there is a thing called digital development in Images Plus. And so what you want to do is you look at it, you'll bring up another histogram chart. Histogram's your friend. And you notice, look at it. Oh, everything's in the dark. And then you bring up digital development and you start the slider control, the automatic, what they call the adjust the breakpoint slider, and you start sliding it. And suddenly something magical starts to happen. That image was there in the previous frame, but you didn't see it. You had to stretch the image. Now, of course, look at Instagram right here. Notice where the peak is, roughly 30 to 40%. That's an optimum image that you want to have. Well, at this point, I stopped in Images Plus. It did most of the heavy lifting for me, or some of the heavy lifting. I then sent it to Photoshop. Now, you can use there's other programs called GIMP, Picture Publisher. There are a lot of other imaging programs, many more that I don't even know about. But I use Photoshop. A lot of plugins are available, and I like to use it. I have a large installed user base. So here it is, here's the result. I see 1396 and the elephant truck, and here's the elephant truck right here. And remember, this was taken with a standard daylight digital SLR. Oh yeah, I may have put a filter in front to help with light pollution. This was taken in the suburbs of Boston. So things can be done even under light polluted skies. Alright, so here are some of the references. These are two of the main references that I use. There are many more, but these are the two big ones. The New CC Astronomy by Ron Wodasky. It's out of print, but it's still around. You can search it out. It's a great primer on CC imaging. Next, and it also applies, a lot of it applies to DSLR imaging. The other, Guide to Astrophotography with Digital SLR Cameras by Jerry Rodriguez. And here's his website, www.astrofix.com. And he's a premier imager. So now let's actually look at some of my images that I've taken. Of course, a supernova remnant, the Witch's Brew, the Veil Nebula. Of course, 52 Cygni is a foreground star, but still very pretty with spikes. Now remember, some people like spikes, other people do not. I mean, it's a personal taste. Remember, I'm doing this for fun. I like to do this. M44 Pleiades. Of course, this looks much better, of course, on the laptop screen and not projected so well. Of course, the classic M42 and the Running Man. And the Horsehead Nebula that you saw in the first slide that we looked at. And now, granted, this was taken in Vermont, and this was over combined image. Each image was roughly 6 minutes apiece, and the total exposure was over an hour and a half, almost 2 hours of exposure time. So that's what the Hubble did. You've seen the Hubble Space Telescope deep field image. Well, that's what they did. They took shorter images, stacked them up to get 90 hours of exposure. We're doing exactly the same thing. M13. Now this one I have to admit, this is a crop, so I have to actually enlarge this image. And all these, by the way, all these pictures were taken with the Epsilon 130. Very wide field, almost 2.5 to 3 degrees of field. Messier 81 and 82 galaxies. Messier 33. Now, one thing about this image, you notice that a lot of you do know that there is hydrogen alpha in the arms. There are actually star-forming regions that show up red. However, DSLR cameras don't pick up the red that well, especially dim galaxies. Now, you notice in the previous images, you saw nebula, they were nice and red. That's because they were very bright, very close by in our own galaxy, and very easy to image. Other galaxies, it's a little bit tough. So someday, if I ever get another camera without the infrared blocking filter in it, I will then re-image this and hopefully get the hydrogen alpha in spiral arms. That'll be another project, something to look forward to. Here's hydrogen alpha, the North American Nebula in Cygnus. Now for the sharp eye among you, you're going to see a meteor trail going down through here. And that's in one slide. I just happened to, while imaging one 5-minute image, it had the double cluster in Comet Hartley 2, just not too long ago. And one nice thing about digital SLR cameras, single shot cameras, you take an image and it's a single image, you capture it. You don't have to worry about shifting the filters, to get the RGB. You take one shot and you got it. And this was actually a number of shots. It's actually more than 5 shots. But I took them in rapid succession, so I was able to image the comet. So the comet didn't appear to move that much, but you still got really good resolution in the double cluster. And of course, the old, the elephant trunk again. Thank you very much. Any questions? Yes, over here. How many okay, so the gentleman asked how many frames I take and how long?
Right, and how do you choose between how long exposure for each frame versus how many frames?
Okay, what it is, basically, you want to take as many images as you can. That's the step one. You always take that. But remember, I was talking about the histogram. You look at each night, you look at the histogram level, and you say, okay, I can take this one a 5-minute shot. And typically in Vermont, 5 minutes is easy. You can take a 5-minute shot and it'll give you a nice 30% histogram in this DSLR. But essentially, you take as many as you can throughout the night. Now, in the summer, it's hard. I can't take many shots. It's also your telescope, whether your telescope can, if it's a solar telescope, let's say f10, well, you're going to take a lot more, imaging time with an f10 as opposed to f2.8. Now, I can take a 5-minute shot, but at f10, you may have to take a 20-minute shot to get the same 30 to 40% histogram level. So it really kind of depends on the night and your telescope system. Okay, another question? Here in front.
You mentioned the Canon D20D has mirror lockup and USB. Do the newer versions of that camera also have mirror lockup?
With Canon, they all do. Yes.
And they all have the USB?
They all have the USB interface, even the inexpensive Roll series. Question? Oh, there, right. I have not, but there was a Sky Telescope article talking about that very thing. And you probably should talk to Artie Hendon about that, who's listening to us here, and he would probably answer you better on that score. Okay. Question over here.
I understand you already retain your flat fields during twilight.
I do. One second, excuse me. I do. That's only because I don't have a flat field box. You can create what they call flat field boxes, in which you can put diffusers in, a light source, and you can have a really nice, and you can take it any time of the day or night. I take it at dusk because you don't have the bright sunlight coming into your optics, because that's going to skew your results. Also, dusk is really nice because I point to the northern sky and make sure there's no light coming in from the side. And so that's the best way to do flat fields during the dusk or dawn. You can do it at dawn also. And some nights I'll say, okay, well, it's 3 in the morning. Okay, I might as well wait until dawn to do my flats. But I still use the T-shirt because you need that diffuser in front. You don't have to use a T-shirt, but it's a real inexpensive thing you can use. White muslin sheets they use the bed covers. You can use diffuser plastics. You can use laptop screens if your telescope is small enough. So I use the dawn or dusk flat because it's a nice even light source, and that's why I use it. Okay, another question? Any questions? Okay. Oh, one over.
You have a website?
Unfortunately, I don't have a website yet, but I've been posting them at the Amateur Telescope Makers of Boston website. So atmob.org, and if you need the address, if you can't remember, I have a few cards that I can hand out. So if you need to go to the site, you go to the gallery section, and a lot of my images, you look under my name, and you will see some of the images up there. I don't have a website. Someday I will. Again, it's on the short list, but I haven't done that yet. Okay, anything else? Okay, over here. Yes. 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 The question is, can you buy flat field boxes? And the answer is yes. There are commercially available flat field boxes. It's better if you make your own. You can get a couple of plastic diffuse screens and foam core, white duct tape, and you can make one yourself. Light source. A light source of say a flashlight would probably work out and make a couple of nice diffusers. But yes, they are available. I don't know these sites. There are a few out there. Just go on the web and look them up, and you can find them. Yes, over here. Go ahead. Okay, in my case with the Canon 20D, I use 800 ISO. And that's because it's an older camera. The electronics weren't as sophisticated as they are now. But with the newer cameras, I think you can go up to almost 1200 ISO. Again, experiment, try it out. I mean, you'll know if it's noisy. You'll start to get all these artifacts in your image, and you'll notice you can't flat field or dark slide out these images, and you realize, oh, that was probably a little bit too much. You see all these bad pixels or white pixels or hot pixels, and you say, okay, maybe I went too far. And you'll know. Again, take a lot of pictures, and it'll be easy. You will know. But 800 for the 20D ISO, and for a lot of the newer cameras, I actually think that 1200 ISO would probably work. Okay, anybody else? Questions? Oh, I'm back here. Yes. Oh, say it again, sorry. Yeah. Yes, I'll probably post it on the Amateur Telescope Makers of Boston website once I get permission to do so. I don't know if Stellafane's going to do it, but I'll find out.
Yeah, all the thoughts are on the web.
Okay, so they said that they are going to post it on the Stellafane website. Question? The limiting magnitude of these exposures? I haven't actually calculated it out, but I interpret just as a reference guide. I guide on 9th and 10th magnitude stars. That's what I guide on. And I can see them in my cameras. And so I know it's a lot deeper than this. This image is a lot deeper. I just haven't gone through that exercise and looked at it. That's something we're going to do on my short list. Okay, one more question? Okay, thank you very much.